Today, we are discussing about design and engineering, secure and fault tolerance enterprise systems. First, welcome to this deep dive into resilience engineering, a critical job in modern enterprises. Today, we are exploring how to build systems that not only survive failures, but actually thrive under pressure. This is practical session grounded in real world distributed systems, challenges to at enterprise scale. By the end, you will have actionable strategies to implement in your own architectures. Let me introduce myself. My name is Rag. I am working as quality performance engineer at Akshay. I bring 10 plus years of experience in enterprise scale distributed systems. My focus is mainly on performance optimization, reliability engineering, and DevSecOps practices. I specialize in building resilient architectures that balance three competing demands: security, fault tolerance, and operational efficiency. I work extensively with complex microservices environments where one failure can cascade across your entire platform. I have debugged systems serving 30K requests per minute. So the challenge modern distributed systems under pressure. There are three critical pressures. One is security threats, second is cascading failures, third is performance demands. The first related to security threats. We are seeing evolving attack vectors specifically targeting distributed architectures. Example, attackers exploit microservice boundaries where security controls are inconsistent. It's a vulnerability in one service can propagate across your entire mesh if not properly isolated. Cascading failures. Single point failures don't stay isolated anymore. They propagate across microservices. Database correction pool exhaustion, memory leaks in dependent services, and ultimately your entire platform cascades. The domino effect makes saying service A fails, service B timeouts, and due to this, service C tries aggressively, which causes resource starvation, and entire system will collapse. Third threat, performance demands. You must maintain reliability under variable workloads. Example, Black Friday traffic is the next year baseline. Security instance clear traffic spikes, your system must handle both gracefully. You want to stand up to say cost, but can't compromise reliability. What is resilience engineering? So, the core definition of resilience engineering is about engineering systems to maintain secure and reliable operation under adverse conditions. This goes beyond traditional fault output. The key insight is it's not just about surviving failures, it's about adapting to threats, recovering gracefully with a three-part foundation. First is proactive design. Don't wait for failures to happen. Design your system assuming failures will happen. Step 2. Security integration. Combine security controls with reliability mechanisms, not afterthoughts. Reverse distribution systems. Control systems that work reliably across complex microservices environment. Example for this is for traditional approach, it's like building a service, monitor it, and react on it. But as part of design and engineering approach, assume the service will fail. How does the system handle it? What mechanisms prevent test? Can we recover automatically? So there are core fault tolerance mechanisms, and there are three mechanisms. One is circuit breaker patterns. Second is retry logic. Third is redundancy calculations. Let's discuss one by one. So circuit breaker patterns. So the problem we are solving here is when a downstream service fails, clients keep forming it with requests, making recovery harder. Resource waste, slow recovery, and customer facing time. The solutions: a state-based model that detects failures and prevents cascading errors by temporarily halting requests to failing services. Think of it like an electrical circuit breaker. When current gets too high, it trips and stops. But there are three states: closed state, open state, half open state. In closed state, normal operations request flow through. In open state, failure threshold exceeded, then circuit clicks and stops sending the request. Of open state. In this, we test recovery with limited requests, like sending one or two requests and checking whether the service is up or not. Let's take an example. Your microservice handles 1,000 requests per second normally. Database crashed, so response time spiked to 300 seconds or 30 seconds. After 5 consecutive failures, circuit opens, so no more requests sent to failing service. After 30 seconds of open, we'll send one or two requests to DB to check if the circuit closes and traffic will resume. They open and we'll try again after 30 seconds. Connecting retry logic. So the problem here is transient failures are common in distributed systems like network hiccups, temporary resource contention, etc. This can create thundering for all plans retrying simultaneously, overwhelming the system. So the solution is exponential backoff strategies that intelligently retrain failed operations without overwhelming the system. Each retry waits longer than the previous one in exponential, like 1 second, 2 seconds, 4 seconds, 8 seconds, 16 seconds, in that. So return in that randomness, so all the plans don't retry at the same moment. Example for our system is API call failed due to transient network error. So the first retry happened at 100 milliseconds. It will wait. And then next retry will happen at 200 milliseconds. And then third retry will happen at 400 milliseconds. So by the time you get to the retry, you're waiting 1.6 seconds, giving the system time to recover. Reducing delay intervals prevent cascading retry. The key benefit of this is transient failures 70% succeed on first retry and exponential backup. You recover from temporary failures without adding stress to already struggling systems. Next is redundancy calculations. So the concept of this is active, passive, and active deployments, ensuring continuous availability. No single mission posts the entire load that there is. So there are two deployment patterns, active, passive. In active, passive, primary server handles all traffic. Secondary server stands by one standby. Example, master slave database server. No primary failure or on primary failure to secondary in 10 to 30 second recovery. Active. Multiple servers actively handle traffic simultaneously. Load balancer distribution request. So example, 3 identical kernel processes each handling 1/3 of the traffic. One fails, the remaining 2 observe the traffic with grace, perhaps with 50% slow, not complete outage. Here get a distinction. There is a real example. So recently, or if you take an AWS, we can see that there are data centers that are present in different regions, like US East, West, EU, China, everywhere. So if AWS US East has an outage, US West and EU keeps serving customers. So RTO, recovery time objective, it's near zero. Users don't notice. RPO, recovery point objective, minimal data loss while replication. Load balancing across replicas. You have 3 identical services. Distributed traffic will be 33% to each. Health checks ensures failed instances get removed from load balancing. Automated scaling as load increases, it will spin up more instances. Let's go in depth in circuit breaker pattern in action. Okay. So, first state. Here we see normal operations. Requests are flowing normally. System is healthy, metrics are green, customers are happy. This is 99% of the time in a healthy system. Stage 2, open state, failure detected. So failure threshold exceeded, circuit trips. 5 consecutive failures happened and the circuit got open. No request will be sent to the failing service. Return fast error response to clients, saying service temporarily unavailable. This is crucial. Stop wasting time. Stage 3. Off posted. Testing recovery. We are testing recovery with limited requests, like sending 1 or 2 requests to see if the service. If both succeed, reset circuit to closed. Full recovery. If posted, circuit stays open, we'll try again later. Stage 4. recovery, return to normal. So now the service has recovered and is successfully restored normal flow. Once service healthy, circuit models complete. Full traffic will be resumed when customers see normal service levels. Business impact due to thesis. Without circuit breaker, outage loss 5 minutes plus 15 minutes recovery. It will be totally 20 minutes pain. With circuit breaker, outage is recognized in 10 seconds. First fail responses. Recovery happens automatically. User experience impact is minimal. Next is chaos engineering, testing resilience through control feature. So the philosophy is chaos engineering is a disciplined approach to discovering system weakness. One counterintuitive idea intentionally break a system before real failures happen. This is not randomly breaking this, it's hypothesis driven. The definition is chaos engineering proactively injects failures into production like environments to validate resilience mechanisms and security posture before real incidents occur. Example, instead of discovering your disaster recovery doesn't work during an actual disaster, test it intentionally. Key practices. Control failure injection. Example, top of one database replica. You are simulating a hardware failure. Run the experiment for 5 minutes, observe system behavior. The system should automatically fail out to remaining repeat. 2. Hypothesis-driven experiments. Start with the hypothesis. If the cache cluster goes down, our API should still serve requests from the database, slower but next time. Kill the cache cluster. Observe. Does the hypothesis hold? Can we handle it? For how long? Gradual blast radius expansion. So we test in turns, like in week 1, test a single log failure. Week 2, test network partition between two regions. Multi-days failure of multiple critical services. Week simulate security instead, detect and block malicious traffic. Continuous learning and deployment. Every chaos experiment reveals gaps. Example, when cache failed, database was more, we need better rate. Fix the gap, then rerun the experiment. Netflix runs chaos engineering constantly. They pioneered this. They intentionally kill side system production using chaos from chaos experiments and tools. Because of this, they are ultra resilient and competitors who let's discuss of all CAP theorem. Means consistency, availability, partition tolerance. So the fundamental constraint. Distributed systems must choose 2 or 3 properties. This is the hard law of distributed systems. You cannot have all 3. Let's explain each property. Positions. All nodes see the same data submitted. Example, you transfer 100 from account A to account B. Consistency means before the transfer, A has $1,000 and B has $400. After that, A has $900 and B has $600. Never in between. Every query returns the most recent rate. Availability. Every request receives a response. Your system always responds. More returns, I don't know. Availability is equals to example 99.99% availability is tested. Max 43 seconds down per year. Partition tolerance. System continues despite network failures. Example, your data center are split across countries. A fiber gets still continues operating even though the two are contacting each other. The trade-off in this practice, CA systems, it's very rare. It's like consistent plus available, but fail if there is a partition. Example, traditional single data center relational database. Not fault tolerant. So one failure is completely outage. CP systems. Persistent plus partition tolerant, but may not be available. Example, some financial systems prioritize consistency. Money has never been wrong. So the trade-off is if a partition happens, stop serving requests or rather than serve inconsistent data. AP systems. Available plus partition tolerant, but may not be consistent. Example, most modern pop-up services like Twitter trade-off is under partition. You might solve slightly scaled data that service keeps running. So the enterprise guidance is enterprise architectures typically prioritize partition tolerance. It's non-negotiable. They balance consistency and availability based on businesses. For money, choose CP, sacrifice availability for consistency. For social cues, choose AP, availability more important than consistency. So next is observability, unified security and performance planning. So the core concept is you can't manage what you can in your system's behavior in data. 5 pillars of observability and its stage. So performance count, loss, latency measurement. So example of this metric is CPU is costing 45%, memory is 72%, request latency like P99 is close to 200 milliseconds, which is 99% of requests calculating to 50 milliseconds. Error rate is 0.02 percentage. That is 1 error per 5,000 requests. These metrics are collected against using data tools like Prometheus, Datadog, New Relic, Flat, etc. Second is centralized logging. Aggregated logs with security event correlation. Every service generates logs. You collect them in one place. Security correlation. Did we see suspicious patterns? Multi-file logins from same IP, etc. like that. Distributed risk. Above microservices boundaries. One customer click buy now request goes to 7 microservices. There shows order service to Power service to inventory service to fulfillment service. And each link shows timing like order is to 50 milliseconds, payment is to 200 milliseconds, inventory is to 30 milliseconds. Find the bottlenecks while payment taking 200 milliseconds when it should be 10 milliseconds. Intelligent alerting. Anomaly detection combining security and reliability signals, not just threshold alerts like CPU grade by 80% alert. It's not like that. So, detecting anomalies is error rate suddenly jump from 0.02% to 5%. So, it can be an attack or thought. Then latency increased gradually. Unusual geographic pattern. So, it can be DDoS from new country. So, why this matters for resilience? When failure happens, observability lets source detect it in seconds, not hours. Not just what happened. What's up meantime less customer data-driven resilience analysis. We can use mathematics to predict and prevent changes. Move from guesswork to data-driven decision making. There are two mathematical models. First one is Markov chains. Model system states and transaction possibilities to predict failure scenarios and recover ones. Example, a service of distance is healthy where 95% chance is 5% chance fails. State B is degraded. Here 60% chance recovers, 30% boss failure is completed. And state C is a first step, 100% chance must recover. If probability margin to predict, if one service has 5% failure probability, what's the probability 3 services all fail simultaneously? The answer will be 0.0125%. It's very extremely fair. Helps you understand where redundancy helps most. The second mathematical model is QE theories, request patterns, service rates, or resources capacity. Example, we have a incoming request 1000 per second, and the service capacity is 400 per second. Average weight that is 4 milliseconds. Calculated using QE. But if request gets talks saying that QE will build up and the weight then becomes 100 milliseconds and customer. So fuel theory tells us you will need at least 400 capacity. They stay below 15 milliseconds states. Real example for the mechanics is, let's say, system can handle 25,000 requests per minute. That's 490 requests approximately. If traffic spikes at 1,000 requests per second, you need to scale up. Queuing theory models request weight among servers needed. This was why is These quantitative approaches enable objective comparison of resilience strategies. Example, should we spend $50K on your active readiness or $30K on care? Maps will show by setting reduces downtime by 15 hours per year and chaos in delivering for 30 hours per year. So we just chaos in delay. Integration challenges in yes, element. So the first challenge is technology stack diversity. We have multiple languages, tables, and platforms for unified design approaches. In the real scenario, every application will have different frameworks. Note a payment service can be Java, Spring Boot framework, Tech service, Python, or Fast API. Then mostly will be React or Node.js. Database will be PostgreSQL, etc. Message will be Kafka. Each has different senior modes, modern tools, recovery drivers. The challenge is to implement unified security of your product across all this. The solution will be like use boxes slash pattern. Example, Istio service mesh. It's handles circuit rating with past challenge legacy system constraints. Wanting components limited for boundless capabilities. Ready productive bounders. Example, you have 20-year-old maintenance developers. Don't add circuit with logic. Don't add estimated place. You can't do notice. The solution will be blocking it with modern resilience layer like API gateway, replace etc. Challenge 3. Security falls enforcement. Consistent security controls across this product systems, boundaries, and procedures. Challenge is how to ensure all services inputs and different authentication audit mode. So parent service might use what tech service might use API keys, legacy system might have no more. The solution is implement security policies that mitigate gateway service. Challenge will be operational context. Managing resilience mechanisms without over engineering. When you implement circuit breakers with almost redundancy and chaos testing, each team needs to understand these concepts. Each service needs configuration tuning. And the problem is configuration will be formed inconsistency at team will burn. The solution will be standardized platform, service mesh, managed Kubernetes, UI handle found patterns. Resource optimization without compromising delivery. So, the balance. You need to scale for peak traffic, example, 50,000 requests per second or platform. But you can't afford to run a peak capacity 365 days per year. So, solution will be optimize resources with optimizing delivery. First, it's baseline measure. Establish performance and cost. So, run for a no for the like average traffic, 2,000 requests per second. Peak traffic, 8,000 requests per second. At the cost will be $50,000 per month. Availability is 99.94%. And error rate is 0.0. This will be your basement auto story. Second, identify inefficiencies. Look at overprovision or underutilized resources. Example inefficiencies will be database has 16 CPU cores, but it peaks at 30% utilization. It is overprovision. API gateway has expensive single certificates, but all this traffic only needs 40% of its capacity. Caching layer data too aggressive to use bigger cache. Reduce database to 8 cores, still handle peak circuit data. Right size and impossible. Apply out of scaling safety mark at 60% CPU utilization. Everyone needs to use server. Remove one server. Everyone only done 3 servers. Black Friday you can scale up to 8 servers. On January again you can scale it back to 8 servers. Safety markers. Both came to exact enough way. Keep 20% better for step 4. Continuous violation. Ensure optimizations maintain SLAs. After optimizing machines is availability still 99.5%. If the drop to 99.84%, optimization is if it is optimization of is latency P99 still below 250 milliseconds. Increase to 200 incidents. It is not capacity. Is error rate still 0.03%? It is timer to this. Example, new car fake and I maintains SLS and cuts costs for $50 a developer. This will be like 144 per year. It is so actionable resilience strategies. So we have first strategies, and we can dive into each strategy. The first strategy, defense in the layer multiple security and form orders. Don't rely on single content. Example, layered work, network failure, taking blocks, all rate limiting, and then layer 3, circuit breaker, drops, cascading failures. Layer 4, retry with backup. So here we have the transient failure. Layer 5, redundancy. Layer 6, automated signal. So you can check all health checks. Layer 7, chaos testing. So this will validate all the links 1 to 6. In real scenario, if one layer, others still protest. So start hitting your chaos test. Example, Reaper, Q1 database, system should weaken simulate network partition between regions. System should operate and take data like perfect intelligence norm. System should and this simulate security breach. Monthly incident post quarter to learn from business. Strategy 3. Automated recovery. Implement self-cleaning portals. Self-cleaning portals. Example, pod thresholds, Kubernetes or clear instances. Database name, modern leak browser service instead. Automatically brain all the connections. Run book examples. If latency exceeds 1 second, first check CPU, second scale or third clear cache, fourth trigger alerts. If overnight exceeds 1%, top roll by latest technology, check logs, then incident declare. Strategy 4. Unified observability. Common security and performance data. Example, we'll have dashboards where for performance, latency, error rate grouping, and particularly log failures, unauthorized access errors, malicious traffic logs. Correlation will be the error rates like correlates if traffic spike. For example, it can be possible video, uniform alert, trigger alert, or combined signal, security plus reliability. Strategy 5. Continuous improvement. Learn from incidents and near miss. After every incident, nameless postmortem should be done like not who failed, but why he failed and what failed. We need to check. Examples, but there that didn't open fast enough. Let's registration. Time, chaos, test, negate. Security incident showed me a missing work. Gets added. So, but time to detect, time to respond, time to recover. Improve each quarter. The key takeaways. Recovery work, resilience engineering, integrates security and reliability. Fault tolerance mechanisms must work in harmony with security controls. Don't play resilience and security set. They must work together. Two of the same can be exploited as ADOS attack. Keep opening and it will keep on opening sinister. Monitor if circuit opening pattern is suspicious is very important. Database. Observability enables faster detection and response. Informed monitoring of security and performance signals accelerates incident resolution. Observability detect problems in 10 seconds. It's worth 30 minutes. Faster detection is equals to faster response equals to is customary. Example, without observability, that's 30 minutes to realize payment status is down. And with it, 30 seconds. Takeaway 3. Chaos engineering validates assumptions before production incident. Controlled failure injection reveals weakness in system design. Don't disturb by most failure swap than it does. Every chaos experiment prevents a real incident. Example, chaos test when database backup is typed. Fixed before it is mattered. Don't wait till it becomes a real issue. Data-driven models provide objective goal. Mathematical approaches enable quantitative comparison of resilience strategies. Use Markov chains and cubic data to provide objective decisions. Instead of quoting which should scale to 10 servers, you can say map shows we need 8 to 10 servers for this traffic pattern. Enable partners conversation with stakeholders.